So chapter 6 today, this week, actually chapter 6, and two important announcements with regards to chapter 6 and the final. We'll begin chapter 6 today. Chapter 6 has 3 homework assignments. Okay. I will introduce the concept, talk a little bit about the background theory, and I'll do an example in class today. Homework, the first homework assignment for chapter 6 would be exactly the same as what we are doing here. So it's 2 questions. The first one is short answer questions based on concepts. And the second one is a problem that is going to be very similar to the solved example in class. It shouldn't take you longer than 15 minutes to get that homework done. So if you have some time after class today, after 12 noon, I would suggest while the material is still fresh, go ahead and complete that homework. So 3 homework assignments, and we will have 1 more quiz next week based on chapter 6. But I will not assess chapter 6 on the final exam. Okay. So the total assessments for chapter 6 are the 3 homework assignments and the quiz next week. And that's it. Then you'll be done with chapter 6. It will not be on the final. Okay, not going to assess it separately. All right. So those are the 2 announcements about chapter 6, frequency response. Final exam page, if you haven't yet looked it up, there's a final exam page and the link is from the front page on the Canvas website. It's been up there since the beginning of the quarter. You students have 4 options to take the final. Okay. All of the information is on there. 4 options is basically the times and the dates that you can take the final. The first is, of course, you can take it at its regularly scheduled day and time. Okay, which is right in this class according to the university's final exam schedule. You can also take the final with the other 2 sections if you need to, or if you wish to. And then there's a Saturday final that is before finals week, meaning the Saturday after the last day of class. And several students have already signed up. Several students actually signed up in the first week of class itself. And so that will be in a different location. It will not be in this building. It will be in the EA building right where my office is. Okay. So again, the location is not finalized yet. But if you wish to take the Saturday final, or if you wish to take it as a section other than this one, then you simply fill out the form that's on the website. And I will make sure that I'll accommodate as many requests as I can. Every quarter I do this and I've never had an issue. Okay, again, students have 4 options. You can take it at the regular time, or you can take it at any alternate time. If you wish to take an alternate time, it's first come, first serve. But again, I've never had an issue accommodating as many students who wanted to take the early final. All right. Okay. So again, go through the finals page and then let me know if you have any questions. Frequency response. All right. What comes to mind if you see something like this in real life? Someone thought it looked like a washing machine. It does, but if this doesn't look familiar to you, you need to get out a little bit more on Saturday nights.
Speaker.
It's a speaker, yes. And engineers are known for studying hard, for working hard, but also known for partying hard. So again, this should look familiar to you. What is this big speaker called? Your kids really do need to get out more. All right, the big one is known as the woofer. The smaller one is known as the tweeter. Not the Twitter, but tweeter. And the big rectangle is kind of like the mid-range horn tweeter. Each one of these has a function. This is known as a 3-way speaker box. A 3-way speaker box. And each one of these speakers has a function. The woofer reproduces the low frequencies, okay, which is the loud thumping noises that you hear in your music, the deep bass, the explosions in action movies. And so these are low frequencies. reproduces the bass sounds. Tweeter reproduces the high frequencies. And mid-range is for mid-range frequencies or vocals. Okay. Now, when we talk about low frequencies, they can be order of 50 hertz to 500 hertz, perhaps. We also have subwoofers. Subwoofers reproduce frequencies. Subwoofers are separate because the lower you go in the frequency range, the wavelength is inversely proportional. So it requires larger and larger dimensions of speaker sizes. Like good subwoofers will start at like 12 inches or larger. Okay, just because of the amount of air they have to move, it requires a lot of power. And so it needs separate power supplies with a separate amplifier. That's why if you have a home theater system, the subwoofers are usually separate. Okay, it just requires a lot of power and a big space to actually move all of that air. Oh, anyone have a subwoofer in their car? Anyone has a buddy who has a subwoofer? I'm disappointed in this generation. I had 2 in my car. Now, granted, it was a beat up old junker, and I purchased the speakers from Walmart, but I did the wiring myself, and that's a long time ago. I don't have it anymore. But anyway, coming back to the point, if you look at the back of the speaker box, you'll see only 2 connections, which is basically one cable or one wire going to it, right? You could take any speaker, even the speakers that we have in this hall right here. If you look at the back, you'll see speakers going into the ceiling. There's just one wire that goes into the ceiling. When you exit the room, you can take a look. That one cable has 2 wires, 2 individual wires, right, to form the connection. And then if you open up the back of that speaker, you will see that this input wire actually goes into a circuit. It goes into a circuit. Now, depending on the cost of the speaker, the design and the components being used, it could be very small or it could be very large. Like small, tiny speakers, not like these ones, but the ones you get for home theaters would actually just have like a capacitor mounted on top of the speaker. Be very, very, relatively inexpensive. Something like this should have a decent circuit inside it. And a big speaker box like the like the ones you see at parties, they are professional ones, and they should have like a big circuit inside it. It should have huge inductors mounted, resistors, and some capacitors. What that circuit is doing is it's filtering out frequency signals. And it's splitting up that incoming signal into 3 parts, hence 3-way speaker box. Most speakers are 2-way. So the speakers that you see in the room right here are probably 2-way. You just have a big woofer and you have a smaller tweeter. So tweeter and then the mid-range. This is known as a crossover network. Crossover network, or more technically accurate, it's an electric filter or an electronic filter. It's splitting up the incoming signal into 3 parts, and then each part has a filter attached to it. Okay, the woofer reproduces only low frequencies, so only low frequencies are allowed to pass through that connection. Everything else is blocked. Okay, everything else is filtered out. And the same thing with the mid-range, same thing with the tweeter. Okay, this is an electronic filter. This filter or electronic filters depend or use the principle of the inductor and the capacitor impedance varying with respect to frequency. So inductor and capacitor impedances are inversely or directly proportional to frequency f. ZL is 2 pi FL, directly proportional to frequency f. ZC, impedance of capacitor, is inversely proportional to frequency f, 1 over 2 pi FC, 1 over f. So as frequency increases, impedance of an inductor increases, or the impedance of a capacitor decreases. right? They're opposites of each other. And so you can block certain frequencies, or you can allow certain frequencies to pass through based on the design of the circuit. And these electronic filters are basically present in every electrical device that we use today. Our electronic world would not function without filters. Okay, so again, kind of important to understand what it is and what it does. So again, the frequency of the circuit, I'm sorry, not the frequency of the incoming signal depends on what the circuit configuration is. We are going to study different circuits and the response of the circuits to the different frequencies, and hence the name of the chapter, frequency response. Electrical signals are present all around us, whether it's a wired circuit or a wireless circuit. Okay. Electric signals are present in every electric circuit. And here is a list of the most common ones that we use in everyday life. Okay. The example I like to use is a cell phone. Cellular signals. We have signals actually all around us, right? Wireless signals all around us. We are bombarded with radio signals, FM, AM, television signals, mobile, satellite communications. It's in the air around us. Our bodies are receptors or receptacles for wireless signals. Okay, we can use our bodies as antenna. If you take a regular phone, whether regular wireless phone, whether it's a smartphone or a dumb phone or a feature phone, doesn't really matter. But every phone, if you purchase it from a wireless carrier, the first thing they would say, it's locked to our network. What does it mean? Locked to our network, right? Because it's a frequency that is being broadcast, and that phone would only work with that wireless carrier. So wireless signals or cellular phone signals are broadcast in these frequency ranges. Okay. These frequency, and they call it the airwaves, right? These frequencies are tightly controlled by every country, by the government of every country. And they are hugely or insanely expensive. Government controls the airwaves, right? That's what they like to say. And what they really do is they actually take the frequencies and they are allocated for certain use and certain purposes. So for instance, the US government opened up the 2.4 gigahertz frequency for consumer usage a few decades ago. And from that point on, 2.4 gigahertz was used for pretty much every consumer application. So you had, I think, not microwaves, cordless phones when they first came out, they would work at 1.8 and then 2.4 gigahertz. Wireless routers, when they first came out, would work only with 2.4 gigahertz bands. A few years later, it opened the 5 gigahertz band also for consumer usage, and started dual band wireless routers started coming out. So your Wi-Fi network had 2.4 gigahertz as well as 5 gigahertz network. What it is doing is it's broadcasting your internet at 2.4 and 5 gigahertz frequencies. Okay, so similarly, these wireless companies, T-Mobile, AT&T, and Verizon, the three big ones in the US, they have to purchase these frequencies from the government. And only they have the right to broadcast a signal at that particular frequency. If an individual or a person uses that frequency and broadcasts at the same frequency range, then it's illegal and they could be arrested for that. So no one else is permitted to use that. That's how they keep everything separate. Yet the signals are all around you, right? If you purchase a phone from Verizon, they will say it's locked to our network. Yet it is capable of working anywhere in the world. Like my phone is a global phone, and it has pretty much all the frequencies. But if you buy a unlocked phone here in the US, and you can buy unlocked phones here, it would work anywhere in the world. So they are capable of working with all frequencies. It's the companies that actually lock it down. And the way they do that is by changing a setting on the phone or changing a setting at their end. And it stops these incoming signals, it filters it out, it blocks it out. So filters are one way of doing that. There are many other ways that they can block it out. They can simply blacklist it or something in your system and it doesn't work. Electronically speaking, it's a filter. A Verizon phone will filter out AT&T signals and T-Mobile signals. A T-Mobile phone will only allow T-Mobile signals to come in. It'll block out everything else. Okay. And so that's how it works. I mean, that's how that blocking thing works. AM radio stations and FM radio stations have a fixed frequency spectrum, right? Have a fixed frequency spectrum. So if you have ever tuned into an AM radio station, perhaps 680 AM or 101.7 FM, that number has a technical purpose. It is actually the broadcasting frequency of that particular radio station. So 680 AM is broadcasting at a frequency of 680 kilohertz. When you set your radio to 680 kilohertz, it is actually filtering out everything else except 680. So it blocks out everything else. 101.7 FM is basically the FM radio station that is broadcasting at a frequency of 101.7 megahertz. Again, high frequencies, but then we are into the gigahertz and terahertz range, right? Let's see. So that's a little bit of general knowledge, but let's see what we are going to study in this chapter. Okay, so far in circuit analysis, we have worked with circuits that look like this. You have a source. The source is connected to a resistor or an inductor or a capacitor, multiple components. And we are used to thinking in a certain way, meaning we are used to determining the voltage across each component or the current through a component, right? Now, we are going to approach this or think about this in a little different way. We know that a source has two terminals, right? Positive, negative. If we pair those terminals together, we get what is known as a port. Okay? Two terminals connected together, we reference it as a port. And so this is the input port, meaning the input signal is going inside the circuit from that point. And at any point where we take a measurement, we can extend this and say it's a measurement. And we can label it as an output port. So if we separate out the input and we separate the output, and we take the circuit and we put it inside a sealed box. If we put the circuit inside a sealed box, we don't know what is inside the box. We don't know what it does. It is opaque to us. Okay. And we don't really care what it does. I'm sorry, we don't really care what is going on inside the box or how it is working or why it is working that way. We only need to know what it does. We don't care what is going on inside the box or what it is made out of. So again, it's a sealed box. It has an input port to receive the incoming input signals, and it has an output port to deliver it to the next stage. But we don't really care what is actually going on inside it. And that's how we are going to look at the filters or the filter circuits. That's how we are going to analyze each one of these circuits. So what is an electronic filter doing? Well, as we talked about, we have so many signals coming in at the same time. What it is doing is it breaks up, or it doesn't actually break up the signal, but it affects each of these signals differently depending on the design of the circuit, depending on the frequency of the incoming signal. So an incoming signal could have multiple components, hundreds and thousands or hundreds of thousands of components. What it does is it treats each one differently depending on the frequency of each component. So as an example, we have V in here, which is comprised of only two parts, V in 1 and V in 2, right? Now, the design of the circuit is such that it increases V in 1 and decreases V in 2. Okay, we want V in 1 to be transferred to the output, but we don't want V in 2 going to the output. And so V in 1 is being increased or amplified, and V in 2 is being decreased or diminished. And then it sends it to the output. Okay, So it's filtering out unwanted components. It's filtering out unwanted components. So it strengthens a particular component and it weakens some other component. It's basically working as a filter. Okay. And so the quantity that relates the input to the output is known as a transfer function. Again, it's a sealed box. We don't care what that box, we don't care what is inside the box. We don't care how it works. We only need to know what it does. And since I invented this mathematical quantity, I named it after myself, h of f. It's not really true. It's just, I think it's just arbitrary. I think they ran out of letters. They were working with like A, B, C, D, E, F, G, and then H was the next in line. So they used H. I haven't been able to find a concrete answer to this. There are, one answer I found online was that it's named after a German physicist, but I don't know if it's true or not. Anyway, h of f, the first thing we realize about h of f is that it's a function of frequency. H of f, right? It's a function of frequency. It's frequency dependent. It is simply the ratio of V out to V in. And if you look closely, it is showing you the phasor symbol. It's the phasor. So it's the ratio of the phasor voltages. It is simply describing how the input is being transferred to the output. Okay, input being transferred to the output, hence the name transfer function. Transfer function is simply describing how the input is being transferred to the output. It's simply the ratio of the output voltage to the input voltage in phasor form. Transfer function. And because it's a ratio of phasors, it's a complex quantity that has magnitude as well as phase. Right? Phasor for V out and V in, they both have magnitudes and phase. So H of F also has magnitude and phase. And because it's a ratio of voltages, it doesn't have any units. It is dimensionless. Okay, no units. It is dimensionless. It's simply describing how the input is being transferred to the output. Make sense? As an example, let's use the audio analogy. If we don't know what this box is doing, but we do know that it's an amplifier and H of F for that amplifier is 2. Right? If we know H of F is 2, we can calculate what the output would be no matter what the input is. We already know what H of F is. Now, for any incoming V in, we can calculate the output V out. Make sense? So again, we don't need to know how or why or, how it's working or why it's working like that. We are not doing any circuit analysis inside it. We are treating it as a sealed box. We only need to know what it is doing and the descriptor, which is H of F. And that's it. We calculate the output. All right, let's take a 10-second pause before we move to the example. Let me know if you have any questions. Any questions before I get to the example? All right, so then let's look at the example. No circuit is given to us in this example. The only thing that's given us is a graphical description of H of F. And the graphical description is in 2 parts. The part on the left shows us the magnitude. The one on the right gives us the phase. Again, it's a complex quantity, right? So the figure describes the transfer function for a circuit We are asked to calculate V out of t as a function of time if the input V in is, if V in of t is given by the expression 3 plus 2 cos of 2000 pi t plus cos of 4000 pi t minus 70. The homework problem is exactly the same as this one. Well, I mean, the graph is different, of course, but it's exactly the same. The approach is exactly the same. Okay. So h of f is described graphically in these two illustrations. We are asked to determine V out as a function of time if V in of t is this expression. So first thing is to determine how many components this input signal has. How many? 1, 2, 3, 4. See 3 as the common answer. That's 1, that's 2, and that's 3. Okay, 1, 2, and 3. If you have a number, there's nothing else attached to the number. It is not a function of time, but it still has a value, right? And because this is describing voltage, it would simply mean there is a 3-volt component, 3-volt DC component in that input signal. So it's not a function of time. Frequency is 0. That's all it is. Here you have, we equate this with Vm cos omega t plus or minus theta, and we extract information. But if it's simply a number, that's a constant DC voltage. So let's identify by equating this with Vm is not Vm, sorry. V of t, voltage as a function of time, cos omega t plus or minus theta. All right. I'm going to break this down into 3 parts: V in 1, V in 2, and V in 3. So for V in 1, value is 3 volts. Frequency F is 0 hertz. Frequency F is 0 hertz. The reason I want to extract the frequency information in F in hertz is because the graph describes the transfer function as a function of F in hertz. Okay. If it was described in omega, it would be H of omega. Then I would simply take omega as it is. I would not need to find F. Make sense? Which is something you might see if you take 321. EE 321 would work mostly with H of omega, okay, not F. All right, V in 2 is 2 cos of 2000 pi t. So F here is, again, remember, omega is equal to 2 pi F. So F is equal to omega over 2 pi. This becomes 1000 hertz. When you are trying to find omega, be very, very careful not to omit the pi if it's given in the question. Sometimes students, I've seen students make that error. Okay, they would simply take the number 2000 and say omega is 2000 because the symbol doesn't register. But anything in front of the t is part of the omega. Remember, it's cos of omega t. Omega is everything that is before that t. So it's 2000 pi and not just 2000. Okay. So be very careful about that. V in of 3 is cos of 4000 pi t minus 70 degrees. So F is 2000 hertz. Okay. 0, 1000, and 2000. And at the same time, I will write the phasor for V in 1, 2, and 3. So for V in 1 is simply 3 volts. V in 2 is 2 with a phase angle of 0. And V in 3 is 1 with a phase angle of minus 70. Okay. This is the information I'm extracting from V in of t. So far, so good? Yes. Yes. Mm-hmm. So we equate each input component with the standard expression. Right there. And so we extract information about the magnitude, Vm, omega, and then the phase. 3 components. Which was today's quiz, by the way? All right, so then we write out the transfer function because the circuit behaves differently at each frequency. So we write out the transfer function at each individual frequency. H of 0, H of 1000, H of 2000. Okay, so H of 0, the magnitude of H of F at 0 hertz is 4. 4. And the phase angle is 0. So it's simply 4. The magnitude of H of F at 1000 is 3. The phase angle of 30. So 3 with a phase angle 30. And then similarly, at 2000, it is 2, the phase angle 60. And see, anything above 1 means that that signal is being strengthened or amplified, right? So until, and let's call this 2500. Until the value of the incoming frequency reaches 2500, the input signal is not diminished at all, right? Beyond 2500, it drops to 0, meaning every incoming frequency signal that is above 2500 hertz is completely blocked. It goes all the way to 0. Everything else is allowed to pass through, and especially lower frequencies are amplified. If it's at 0, it's magnified or amplified by a factor of 4, right? That's a transfer function 4. So all that's left to do is perform simple multiplication to obtain V out. So V out 1 would simply be H of 0 times V in 1, 4 times 3, gives me 12 volts. A constant DC voltage. Constant DC voltage. V out 2 H of 1000 times V in 2. And that gives me a value of 6 with an angle of 30 degrees. Again, it's being amplified by a factor of 3. V out 3 is actually not being affected at all in terms of amplitude, since it's being multiplied by 1. Sorry, multiplied by 2. So it is being affected. 1 with angle of minus 70, which gives me 2 with an angle of minus 10 volts. So all 3 of them are being amplified. If there was an input component at 2500 or at 3000 perhaps, or 3500, any value more than 2500, it would be 0, because H at 2500 or more would be equal to 0. So it's blocking all frequencies higher than 2500. It is not allowing the higher frequencies to pass through. It's only allowing lower frequencies to pass through. So it's kind of like a low pass filter, which we'll talk about later. But does the approach make sense here? You're given the description of a network in graphical form. It describes the magnitude as well as the phase. You are given an input signal that is going into that circuit. So you've divided up into individual components, extract the frequency information in hertz, then write down the transfer function from the graphical description, and then simply apply the ratio of the voltages equation to calculate your V out. And then your final answer is asked as a function of time. So V out of t would simply be 12 plus 6 cos of 2000 pi t. That doesn't change. Frequencies remain the same. Plus the third component, 2 cos of 4000 pi t minus 10 and volts. Okay, your homework problem is exactly like this. Yes. Separately. Well, this function, well, we are not concerned with that. Whether it's linear or non-linear, we are not concerned with that. We are just given an input signal that has different frequencies. If you remember from chapter 5, if 2 frequency signals are being summed up or subtracted, the frequencies must be the same. In this case, the frequencies are different, so we cannot actually add them up. So the only thing that this is showing, the 3 plus this plus this plus this, so V in plus 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 plus, all it means in this case is that all of these frequency signals are going into that input circuit all at the same time. That's all it's displaying. And we just treat it separately because they are separate components, we cannot combine them. If the frequencies are different, you cannot combine them. Okay, they have to be the same frequencies. So again, in this case, we don't read too much into it. We just deal it with as 3 separate components or 3 separate inputs that being applied into the same circuit. And that's it. That's all it means.
Professor.
Okay. Yes.
Is the original V in equation given?
Yes.
Okay.
So it's right there. So if V in of t is this component, yeah. All right, so we'll end class here today. I will see you all on Wednesday. If you have any questions, I'm still around for a few more minutes. Again, if you have time right now or sometime in a few hours, while this material is still fresh, go ahead and complete the homework. It is very short, just concept based. And then the second one is the problem that's exactly like the solved example in class. All right. Okay.